We're looking at problem 20.13 here. There's an air-filled toroidal solenoid. In case you forgot what a toroidal solenoid is, a toroidal solenoid is the kind that instead of being a long tube is going to be a circle. So it's going to be as if here is like the tube itself instead of like that flat tube. And then we're going to wind wire around it. So it's going to have wire all across it. Okay. And they tell us a bunch of stuff about that toroidal solenoid. I know mine is not very even. Okay. They tell us the radius of it. They tell us that it's 0.15 centimeters. And they tell us cross-sectional area. Because remember, that's the area if I sliced into this thing. That's what I would get. Okay. And they tell us that when the current is 12 amps, that the energy stored in it is 0.39 joules. And they ask how many turns it has. Well, that's kind of an unusual thing to ask. So we're going to have to actually go through and figure that out. But they give us the energy, and that's actually helpful to us because we know an equation for energy for anything that's for any kind of inductor, and that's going to be 1/2 Li squared. Since they give us the energy and they give us the current, we can solve for what the inductance is. So let's go the self-inductance. So let's go ahead and move that around. So L is going to be 2U over I squared. Now we can plug all the stuff we know in. 2 times 0.39 joules divided by 12 amps, quantity squared. We do all that and we get 5.42 times 10 to the negative third. You can check it on your calculator. It'll be joules per amp squared. If you actually work the unit together and simplify things out, you end up with a Henry. Okay, and that's good. Okay, so now we're going to have to look at the definition for self-inductance to actually figure this out. Self-inductance is going to be, remember, it's going to be N times that magnetic flux per amount of current. Remember, just small I there. We're going to replace that with the field times the area. And because it's a solenoid, we can just use bunny for that. So it's going to be N times mu naught N I times A over I. You can see the currents divide out nicely. That's a good thing. Okay. And we end up with N mu naught. And I'm going to have to unpack this little n. Remember, that is the number of turns per length. So I'm going to put n, and I'm going to divide it by the length on the bottom, A. But this is a big circle going around. So I have to replace that with 2 pi r. That's the length it's going to take. So I'm going to have n squared mu naught A over 2 pi r. All of that's going to be the inductance. So I'm going to have to rearrange like heck to come up with what the actual number here is. So n is going to actually be the square root of a bunch of stuff. It's going to be 2 pi r times L over mu naught A. I brought these to the bottom. These end up on the top along with that inductance. And I take the square root of this term to actually come up with what the number of turns is. Okay, so now I have to plug all my good stuff in. And I have 2 pi times 0.15 meters. L, that's my inductance, not my length, remember. And that's the 5.42 times 10 to the negative third henries. Then I divide it out by the constant, the permeability of free space, 4 pi times 10 to the negative 7 Tesla meters per amp. And I have A. Now, A they give me is 5 centimeters squared, but I need it to be a meter squared. So it's going to be 5 times 10 to the negative 4th meters squared. 10 to the second for each centimeters, and there's 2 of them. So I take the whole thing, and it's kind of a pain, but I have to take my calculator out and do it all. Okay, all right. So if I take my calculator out and actually solve the problem, you can see that first the pi's go away. This goes away. I have just 2 on the bottom. That kind of helps. I have 10 to the negative third and 10 to the negative fourth, so that will actually go away. And this will go away with 10 to the negative 1. I can combine that. This comes 10 to the negative eighth. And when I go to actually multiply, I'm just going to take 0.15 times 5.42. I'm going to divide that by 2 times 5, 10 to the negative eighth. If I take all that and take the square root, I get 2,851, I think. And that's the number of turns. I think if you look it up in the back of the book, it's like 2,850, probably because they kept with the 3 sig figs instead of keeping every digit. So probably it's better to have 2,850.